科技临界点向世界介绍中国科技。
A Chinese-US research team has created a working semiconductor out of graphene for the first time, potentially paving the way for ultra-fast computing beyond silicon chips. For years, semiconductor technologies have relied on silicon, but they are reaching their limits, pushing against the physical boundaries of Moore's law. This has driven the search for new materials that could keep powering advances in computing and electronics beyond what is possible with conventional silicon-based approaches. And that material is graphene. It is a single layer of carbon atoms over 1 million times thinner than human hair. It is also known as the first stable two-dimensional material at room temperature. Compared to silicon, it has greater electronic potential for microchips. Since its discovery in 2004, scientists have worked to combine graphene with other carbon materials to create an energy-efficient, high-speed chip that is better than today's fastest semiconductors. However, there's a big challenge. Despite its remarkable conductivity, graphene lacks something called a band gap. Think of a band gap as a gate that controls the flow of electrons in a semiconductor. When the gate band gap is closed, electrons cannot pass, and the material acts as an insulator, blocking the flow of electricity. When the gate opens, electrons can jump across the barrier, and the material conducts electricity. The graphene lacks this natural gate or band gap. Without a band gap, graphene is like a road without traffic control. Electrons can always flow freely, resulting in excellent conductivity, but you can't stop or regulate them when needed. This constant flow is great for some applications, but a problem for electronic devices like computer chips or digital switches, where you need to precisely control when and how electrons move. Therefore, without a band gap, graphene can't effectively switch between conducting and blocking electricity, and cannot effectively control the flow of electrons, limiting its applications in precise current control. However, scientists have now discovered a method to overcome this limitation. Researchers from Tianjin University and collaborators from the Georgia Institute of Technology have successfully developed a process to introduce a bandgap to graphene, opening up new possibilities for ultra-high mobility semiconducting epitaxial graphene on silicon carbide. By growing graphene on silicon carbide crystals and using a specialized annealing method, they've managed to produce a buffer layer of graphene with a well-ordered structure. They've created high-quality semiconducting graphene with an impressive bandgap of 0.6 electron volts. This breakthrough introduced traffic lights to bandgap at strategic points along the highway, enabling precise control of electron flow and opening up new avenues for advanced electronic devices. At room temperature, this new semiconducting epitaxial graphene (SEG) has mobilities that exceed 5,000 square centimeters per volt second, which is more than 20 times greater than the limit imposed by phonon scattering in other 2D semiconductors, and significantly surpasses the mobility of traditional materials. Picture your computer's processor working 20 times faster, enabling lightning-fast computations and seamless multitasking. This is the kind of advancement SEG brings to the table. Moreover, SEG is also very stable and compatible with current manufacturing methods. It can be easily patented and integrated with other graphene layers, which means that the material can be shaped in precise ways without much difficulties to create intricate and precise design necessary for advanced electronic devices. And this makes it an ideal candidate for next-generation nanoelectronics. While the research is still in its early stages, the group leader, Professor Ma Lei, estimated that it might take another 10 to 15 years to fully realize the industrial implementation of graphene semiconductors. But the breakthrough holds immense promise for various fields, including telecommunications, computing, and energy storage. We can look forward to a future where electronics are faster, smaller, and more powerful.